All right, thank you. So, basically pick up where I left off yesterday. So let me remind you where that was. I want to kind of go through this exercise of seeing to what extent we can understand the second law, where the second law of thermodynamics comes from, by thinking at a microscopic level. And one of the take-home messages of all of this little exercise is going to be that we can actually get quite a lot of mileage out of just out of using Liouville. So let me formulate the problem as follows. So there's Thomson's formulation of the second law, which, as I mentioned yesterday, says the following. You've got a thermally isolated system, so by that I mean a system that's not in contact with the heat back during the process, although it is in contact with some work parameter that we're going to be changing. You assume the system is in an initial state of thermal equilibrium, and then you subject the system to a cyclic process, meaning that in your parameter space, you start at one point, move the parameters around some loop, and end up with the parameters back where you started. And Thomson's formulation of the second law says that makes a prediction that the work that you do over the course of the cycle must be greater than or equal to zero. So let's see to what extent we can understand this based on microscopic principles. And the formulation I started off with yesterday involved, well, let's see, x denotes a point in the phase space of the system. H is some Hamiltonian, which depends on this parameter or a set of parameters lambda. And I assume that since the system is a classical system that's isolated from any thermal reservoirs, it evolves under Hamilton's equations during the process in question. So in general, for an isolated classical system, the work is going to be the net change in the value of the Hamiltonian, because no energy is being exchanged with the reservoir for an isolated system. So the work can be written as the final value of the energy, so the Hamiltonian evaluated at the final point in phase space, at the final value of the parameter, which in general is going to be different from the initial parameter, but for a cyclic process, the final value is going to be equal to the initial value. So this is the final energy of the system, and here's the initial energy of the system. And again, this represents some trajectory evolving under Hamilton's equations from some initial condition x of 0 to some final condition x of tau, which is uniquely determined by x of 0. So because everything depends only on the initial conditions, we can write the work as an explicit function of the initial conditions. Now, a very naive interpretation, or maybe a direct interpretation of the second law, would say, well, second law says that this is going to be greater than or equal to 0 for any initial condition. So the question is, can we show that this is true for any initial conditions? And the answer is no. In fact, we can argue that generically there will be initial conditions for which that inequality is not satisfied. So let me start at that. So let me assume, for the sake of argument, that this will be satisfied for any initial conditions, and I'll show you how this leads to a contradiction with Liouville's theorem. So let me draw here a very schematic depiction of phase space. So here are my coordinates, here are my momenta, and ideally I would be drawing this in 6m degrees of freedom, but I can only do it in 2 degrees of freedom. Two variables, so two variables in phase space. And now let me draw a circle here which denotes a given energy shell in phase space. So this is the surface, we call it S0, which is the set of all points in phase space such that the value of the Hamiltonian, or the initial energy, let me call it x0, is comma a, is equal to some constant value, let me call it u0. Right? So I'm looking at all points in phase space that have, all initial conditions in phase space that have the same energy u0. And let me, for the sake of keeping this argument simple, let me assume the following, that all points inside this circle correspond to h less than u0, and all points outside this circle correspond to h greater than u0. Okay? And again, I'm saying circle, but really you should think of this as a 6m minus 1 dimensional surface in a 6m dimensional phase space, where m is going to be the number of particles that I have in the system. So let me now imagine some given initial condition x0 that's sampled from this energy shell as sub 0, and let me imagine that again for any initial condition like that, this equation is going to be satisfied, right? So if I follow a trajectory that evolves from this initial condition through phase space in time as I change my parameters in some cyclic fashion, right? So the trajectory is evolving under Hamilton's equations as lambda is being taken around some loop in parameter space. Then this will end up at some point x of tau in phase space, and because I'm assuming that that inequality is going to be satisfied for every single initial condition, x of tau is now going to be found outside of the circle. So starting on the surface of the circle is found outside. And I can do this for any point on this surface over here. So let me draw out the surface in phase space over here that this set of initial conditions gets mapped to. So it'll be something like, let me draw it kind of like that. And again, I'm drawing this surface consistent with the assumption that every initial condition leads to positive or non-negative values. Okay, let me also make an assumption, which I'm going to drop in a moment. Let me also make the assumption that all the points inside this surface get mapped to points inside this curly surface over here, and similarly all points outside this surface evolve to points outside that surface over there. All right, so I have something that looks like this.
So what are all those points? I missed a little bit. These are different x tau points for different initial conditions?
Pardon me?
The points that lie on that surface, those are different x taus for different x naught?
Yes, but all of them being chosen from this initial
so it's
surface.
sort of the evolution of the circle into this.
Exactly. So this is the this represents the surface to which this initial surface evolves under Hamilton's equations as I'm changing the parameters on the surface. Yeah.
You just said yesterday the phase volume remains constant, even if lambda.
Okay, you're stealing my thunder. So I was about to ask, but you're absolutely right. But that's the answer to my next question.
So have you now made some assumptions about how H depends on P and Q when you draw these pictures?
Yes. Yeah. I'm making a simplifying assumption that basically all these energy shells are nested inside one another.
So there's some monotonicity conditions.
Yeah, there's some monotonicity. Right. And again, I'm doing that because I'm not really trying to make a full mathematical proof. I'm kind of trying to motivate how these kind of microscopic considerations might help us to understand this. So this isn't supposed to be a proof where I'm considering every single possibility, but at least for this kind of generic class of systems. Now, it is true that if you have a Hamiltonian that's of the form kinetic plus potential, where the kinetic is just, p squared over 2 and so forth, then you'll have, every energy, the volume of phase space enclosed by one energy shell contains all energy shells with lower energy. So it's not a really drastic assumption I'm making, but it certainly is a simple.
Wait, doesn't that require G be monotonically increasing in Q?
No, if I want that to be simply connected, I would want B to be monotonically increasing in Q. But even if it weren't simply connected, all I'm saying is, so let's say a particular energy shell might look like this if I have, some kind of double L structure.
Okay.
Still, all the points inside here are going to have energy less than.
Okay.
So that's really what I missed. All right. So having done that, now let me ask the question that was already answered. What's wrong with this picture? And the answer is, well, clearly phase space volume isn't being preserved, right? So this kind of picture over here, where every initial condition on this surface gets mapped to something outside of that surface, and the interior here gets mapped to the interior here, that clearly is a violation of Liouville's theorem. So that's not going to work. All right. Well, you can say, all right, I can get around this a little bit because I really shouldn't be making the assumption that the interior of this region gets mapped to the interior of this region. So that shaded region over there might get mapped to something that looks like this. So I'm trying to draw something that looks kind of like a donut, right? And then as long as the volume of this shaded region over here is equal to the volume of this shaded region over here, Liouville's theorem is satisfied. So is there anything wrong with this picture? Does this somehow simply violate some principles of Hamiltonian evolution?
What would be reversible in the inside part would be mapped to a single point on the left side?
Pardon me?
Since the inside part can evolve back to the left picture, then this volume would be.
I'm not exactly sure what you're saying here, but I think this picture actually is consistent with Liouville's theorem. All right, yeah.
Really? I mean, what about the contour? If I take a contour in the first picture and I shrink it to 0, I can shrink it to a point. But in the second picture, I can't, so we change the topology to a group.
Yeah, I'm changing the topology, but that's fine.
But
When things go over barriers and stuff like that, topologies change. So just because I have this simple topology over here doesn't mean I have to have that simple.
I mean, under simple, like a differentiable Hamiltonian, you can still get topological change.
Yeah, sure. So for instance, if you have a single potential well and you start inserting a barrier into that potential well, then regions can split up and stuff like that. So generically, you can have this. So actually, there's nothing wrong with this picture, in my opinion. This is perfectly in accord with Liouville's theorem. But and if this is the case, then it's true that every initial condition on this energy shell ends up with a higher energy at the end than it had at the beginning. But, and I'll get to these questions in a moment, but if this is the correct picture, then where did the final conditions in here come from? Well, they must have come from outside of the circle, right? So there must be some conditions, initial conditions out here that started out outside of this region and ended up inside of this region. And for this initial condition, then the energy went down. All right. So one way or the other, it seems that in order to be consistent with Liouville's theorem, you can't have all of the initial conditions leading to trajectories for which the energy increases. Some of them have to decrease, except for maybe in the special case where they all end up with exactly the same energy that they started with. Just a question.
Is it possible to make a simpler argument just based on reversibility? And say, all right, well, that equation you wrote down, that inequality, let's just do it backwards and then get the opposite inequality.
It is possible to make a simple argument based on reversibility if you assume that Hamilton's equations are time reversal invariant. So if you assume that there's no magnetic fields in the system. So then you can make those simple arguments. But I'm not going to necessarily assume that. So in other words, I'm not going to assume that if I take a final point here and then reverse the momentum, I'm going to get back to the same point there.
Well, with the magnetic field, you might get a reflection also.
Pardon me?
With the magnetic field, you might get a reflection also, right?
Yeah, you might, but then in order to make that argument very general, you have to do a little bit of work. I'm not saying that this is the only way. That this is the only way to get this result, but this is kind of in my opinion, a nice geometric way to see that Liouville's theorem already leads us to suspect that this can't be true for all initial conditions. Okay, question here.
So, in this particular picture you've drawn where you conserve the volume, are you also conserving the surface area?
First of all, no. Second of all, how are you defining surface area?
The surface. You have a well-defined surface area that encloses your volume in phase space here, and you, in principle, have a well-defined surface area enclosing your volume in phase space here.
There's a well-defined surface, but not necessarily a well-defined surface area. I mean, if I choose to draw this in Cartesian coordinates, and I can define a Cartesian surface area, but it turns out that definition of surface area does not have a particular meaning for Hamiltonian evolution. It doesn't. I mean, you can define it and everything, but it doesn't. There's no reason to think it should be conserved. Something like that. There is a more formal. There is a meaningful way to define surface area for Hamiltonian evolution, and I'm not going to get into that, but it's not something that's conserved.
Sorry, are the initial conditions you're looking at just on the surface, or are you also looking at the inside the disk and outside the disk?
Well, in principle, I'm looking at any initial condition. So this circle here goes to this curly shape over here. The shaded region over here gets mapped to the shaded region over here, and the non-shaded region gets mapped to the non-shaded region. Right? So I've just drawn kind of schematic.
But you're saying that work increase just has to increase for one of these initial conditions. Is that what you're saying? Because I'm just saying that you can map the surface, right, so that it, it's a donut, which is also bigger. But then you're saying that outside of that surface. you will still have points that decrease in velocity.
Yeah, that's basically what I'm saying. One way or another, if you try to push it in one way, it's going to come out the other way, so to speak. One way or another, if you're preserving volume in phase space, if you're satisfying Liouville's theorem, there are going to be some initial conditions whose energy gets lowered during the process. You can't have a case that all initial conditions lead to higher energy. That's the only point.
So obviously you're saying the energy is not conserved here because lambda is a time dependent, so you didn't work.
Yes.
Yeah, so you said something about the Hamiltonian in the interior of the second picture. There's no way so
How can I say what?
How can you say that? Is the Hamiltonian there in the interior? The second picture is lower than on the
well, so first of all, it's the same Hamiltonian function in the initial picture as in the final picture because I'm coming back to the same point in phase space, right? So if I were to draw the level surfaces of the Hamiltonian here, they'd be exactly the same as over there. Does that answer your question? Or I'm not sure what you're.
Yeah.
Okay.
So one thing that we're worried about in this corner is uniqueness, okay? The other thing we learn about Liouville's equations is that trajectories don't cross.
Right.
Is that still true given the work parameter? And how do we know that if trajectories come from the outside and end up on the inside, we don't get a crossing somehow?
Oh, okay. So first of all, the answer to the first question is absolutely yes. Everything is still deterministic. There's no crossing of trajectories. And I don't know if I can simply convince you here that you can go from this situation to this situation without crossing trajectories. But there's, in fact, I could construct a simple, I can think of simple models where you do get this kind of rearrangement of energy shells, but that would take considerably longer to kind of go through each of them.
So you're saying there's a third time dimension because lambda is not the same.
Pardon?
You're saying that it's really a three-dimensional thing because now lambda is independent, so it's conceivable that this area is independent. Because it was two-dimensional.
Yeah. In some, I think I see what you're saying there. Yeah, there's a third dimension.
Because it's a three-dimensional.
I was just going to comment, you need more than two dimensions, and that the surfaces don't create barriers.
I'll provisionally agree with that. I'm not sure I understand exactly what you guys are getting at. But certainly all the dynamics here. Okay, so basically this was just kind of a simple argument to motivate the idea that generically what you're going to get is something maybe that gets mapped to the following situation. Okay, I've drawn it down here not like a donut. But basically this energy shell gets mapped to some surface, part of which is outside and part of which is inside. So some initial conditions lead to increase of energy and some initial conditions lead to decrease of energy. And so if we're going to interpret the second law from microscopic principles, we have to interpret it statistically, right? So the way we have to write it down is not like this for all x0, right? So that's wrong. But rather we have to write down the Thomson's formulation of the second law as follows. The average work, and I'll explain what I mean by all these symbols here in a moment, which is given by the integral of some over initial conditions times f sub a of x sub 0 times w of x sub 0, where w is again the work. It's just a function of the initial conditions. And this f sub a is meant to represent some probability distribution in phase space that's supposed to characterize a system at equilibrium in state A. Okay, so I haven't specified what it is, but it's some probability distribution that corresponds to state A. And now the question is, can we show that this inequality is rigorously satisfied for some reasonable choices of this initial probability distribution? Okay, and I'm going to write down three different candidates. I'm not going to try to justify them, but let me write down three different candidates for this probability distribution and then talk about them one by one. So Number one, I'll denote FA sub u. This is a microcanonical ensemble. So this would be something that's just proportional to h of x0 minus u0. All right. So this is going to be this is an ensemble. It's a phase space distribution that represents a uniform distribution over the surface of this particular circle, but nothing inside or outside the circle. So that's the microcanonical ensemble. I can also consider the canonical ensemble, and you know that's just proportional to the Boltzmann factor, where here beta is some inverse temperature that I can choose. And then let me consider another ensemble, which I tend to call a macrocanonical ensemble. I'm not sure if there's really a proper name for it. But this is just proportional to a theta function. Let me make sure I get this right. U0 minus, so let me be a little bit careful with my notation here. I've been using UA in the notes. So this would be U sub A minus H sub A of x0. Okay. And here the Hamiltonian is the one associated with the parameters, So again, this would be the phase space distribution that's represented by this shaded region over here. So imagine that I choose my initial conditions uniformly from within the interior of this region.
Well, for large dimensions, for large number of particles, because the first and the third are the same, right? Basically, so all the volumes on the.
Yeah. Well, actually, for large systems, all three of these become equivalent. That's something that this equivalence of on the equivalence.
I wasn't talking about equivalent. The size and the understood. But the functional form is almost identical even for large dimensional systems between the surface and the volumes. So everything is out.
Yeah, that's right. That's right. So another way of saying that is if I have a sphere in many dimensions, then almost all of the volume of the sphere is located, infinitesimally close to the surface of the sphere. So for very large systems, we should expect these ensembles to be at some level equivalent. Okay, and I'm not going to go into details about that, but you should be at least aware of that. All right, but now. So if we've defined these three ensembles, can we show that this inequality is satisfied rigorously for these cases? Yeah.
Do you have requirement for the evolution time tau?
Pardon me?
Do you have requirement for the tau?
No requirement. Tau is arbitrary.
But the problem is if tau is infinite, is very small, then we might expect the process to be reversible.
I'm not making any assumptions about it being reversible or irreversible. So for the moment, I'm assuming tau is finite, and I'm assuming the evolution is Hamiltonian, and then I'm assuming that that initial conditions are sampled from one of these distributions, and I'll consider them one by one. Those are the only assumptions I'm making. I'm not making any assumptions about reversibility. All right. So what I'm going to show now is that this inequality can be proved exactly for this choice of initial conditions, right? Then as an exercise, you guys are going to show that it can be shown to hold for that set of initial conditions, at least within the kind of simple arguments that I was making over there. It turns out for the microcanonical ensemble, you can't prove this inequality, because in fact counterexamples can be found. To this inequality. So this does not always hold when you're sampling from a microcanonical distribution. I'm not going to go through that, but let me just work through the details of how you show this is true for a canonical ensemble.
So what's the implication of it not working for microcanonical?
Pardon me? I'm not sure if there's an implication beyond that statement. It just doesn't necessarily work for a microcanonical ensemble.
So you're saying second law cannot be proved with regard to microcanonical?
No, I'm saying that's not going to be a second. That's not equivalent to the second law. Okay. If you think so it depends on how you decide to state the second law. But let me put it this way: if this were not true for a canonical ensemble for some particular system, then I could use that system to build a perpetual motion machine of the second kind. I can't do that for a system that violates it for a microeconomic ensemble.
Okay, because you're saying there is nothing to extract the energy from. In the second case, you can keep extracting it from the back and build it perpetually.
Well,
but in the first case, you're saying
not exactly. It's a little bit like this. So in both cases, it's isolated. So let's say I have something that violates this for a microeconomical ensemble. So I started a microeconomical ensemble, right? I go through one cycle. I get some energy out of the system, right? So then I'm happy. But now I want to go through another. I want to repeat that cycle over and over again to keep getting energy out of the system. Somehow I have to get it back into a microeconomical ensemble. I don't know how to do that without doing work on the system. If I bring it in contact with the heat back, it will relax to a canonical ensemble. Okay, so I'm saying that this being violated does not imply that I built a perpetual motion machine of the second kind, but this being violated would imply.
It's really a constraint of having the total energy fixed all the time.
Well, not fixed all the time, but
right.
sampled from a given energy rather than sampled from. Yeah. So another way of saying is I can prepare a system in this state without doing any work. All I have to do is bring it in contact with a thermal reservoir. I can't prepare a system in this state without doing any work. Or at least I don't know. Yeah.
But it's still true that when you go to macroscopic limit, the deviations, the cases in which microcanonical ensemble doesn't satisfy this go away, or somehow.
I don't know how to prove that, but
well, just from implication from the equivalence of ensemble.
Yeah, that's probably true.
It's just you're saying if a microscopic system, this is not satisfied by the microcanonical.
Right. So let me make the statement a little bit more precise. The counterexamples that I talked about are all in 1 degree of freedom. So I don't know any counterexamples of in more than 1 degree of freedom. And you're right. By the equivalence of ensembles, I would expect that at least in the thermodynamic limit, this should probably work.
Does the counterexamples have odd little limits?
Not particularly, but I really don't want to get carried too much further afield. This was the first 5 or 10 minutes of the session. Okay. All right. So let me try to prove this for sampling for a canonical ensemble. Let me set it up in a very general way. Again, here's my base space, and let me assume that I have some mapping M, which takes me from some which maps some point x in phase space onto some point y in phase space. So for any point x, this mapping will take me to some point y. Right? And I'll assume 2 things about this mapping. Number 1, that it's invertible. So M inverse exists. And number 2, I'll assume that this mapping preserves volume in phase space. So a little cell of some volume here gets mapped onto a cell which has the same volume over here. So another way of saying that is that the Jacobian associated with this mapping is equal to 1. And again, the Jacobian is that expression that I had up yesterday that involved the determinant of this partial derivative matrix. All right. So under these assumptions, let me now define a function capital phi of x0. Capital phi of x, which is going to be my Hamiltonian h of a evaluated at y of x. So y of x is just the y that gets me where I'm taken by application of this mapping from point x. Hamiltonian evaluated at y minus the Hamiltonian evaluated at x. Right? And what I'm going to show is that if the initial conditions are sampled from the canonical distribution, then phi on average is going to be greater than 0. Right? So that for any mapping that satisfies these conditions, if I sample from the canonical distribution, then apply the mapping, on average, the value of phi is going to be positive. Yeah.
What's the condition for the existence of the inverse mapping to just something?
No, This is the condition. In other words, I'm saying that.
What dynamics do you have to have for that to be true?
I'm not assuming this is dynamics at the moment. I'm just assuming this is some function that takes me from one point in space to another uniquely. It's 1-to-1 and onto. right? So if I ask you, if I tell you I got mapped to point Y, you'll be able to tell me, oh, you must have started at X. Okay. Where I'm heading with this ultimately is that this is going to be Hamiltonian evolution, but right now it's just some arbitrary volume preserving invertible. All right, so how do I prove this? And this is a good exercise because this line of proof is going to be very similar to the one that I'm going to use in establishing non-equilibrium work relations later on. So let me look at the canonical average, not of phi, but of e to the minus beta phi. Okay, the average here is always average, canonical average over the over phase space points x sampled from that distribution. So this is going to be integral dx 1 over z e to the minus beta ha of x. All right, z is the partition function here, so this is my probability distribution, and now the function whose average I'm considering, e to the minus beta phi of x. And what you immediately notice is that this h sub a of x here cancels with the h sub a of x that appears here. So let me rewrite this now, pulling the partition function outside of the integral. I have 1 over z integral dx, and what remains after that cancellation is e to the minus beta h sub a evaluated at y of x. Okay? Yeah.
So quick question. So are you sampling x? You're taking x from the distribution, and at the moment we don't do anything with y. Y is just something that x evolves to. Is that right?
Yeah. Y is the image of x under the mapping x.
Okay.
So basically, I'm sampling x from my initial distribution, and then acting on it with the map that gives me a y, and then I look at the change in the Hamiltonian for that thing, and then I choose my next point x and do it again.
I have a question because I don't want to be confused all the remaining of the lecture. When we say that we're having a canonical ensemble, it means we're allowed to exchange energy between the particle and the reservoir. And it means that the system can dissipate some of its energy into the reservoir. In this case, I have dissipation. In this case, I don't expect Liouville theorem to hold.
No. So when this is supposed to be a distribution of initial conditions. So I might use a thermal reservoir to get this distribution of initial conditions, right? But then, pardon me?
The moment you take one, you isolate it?
That's right. After I've prepared these initial conditions, I isolate the system. So think about it this way. I take one copy of the system, place it in contact with the reservoir, allow it to equilibrate, and then I remove it from the reservoir and then place that copy on the table. Then I take another copy, do the same thing, place it on the table. Yeah?
I have another question.
Okay.
In order to make sure I'm understanding things properly. And the other part where you say it's a thermally isolated system, it means if the system loses energy, you're not pumping energy back to the system?
No, all I mean by thermally isolated is that during the process when I'm actually changing lambda, there is no thermal reservoir.
So the system can dissipate.
What do you mean by dissipation? The system evolves under Hamilton's equations, and I'm changing lambda.
Some energy to the environment?
No, because there is no environment. When I say thermally isolated system,
complete energy is conserved.
Pardon me?
Energy is conserved.
No, energy isn't conserved because I'm changing the Hamiltonian as a function of that. Let me give you a specific example. A gas inside a piston, right? So here's my gas, all right? And somewhere out here, I have some thermal reservoir at temperature T. Okay? So imagine that I take this piston, first I bring it in contact with the reservoir. There's some exchange of energy between the two. The system comes to equilibrium, and then I remove it from the reservoir. Once I remove it from the reservoir, it's an isolated system, right? It's evolving under Hamilton's equations. I'm assuming there's no contact between this gas and anything outside of the system, right? So it's an isolated system evolving under Hamilton's equations. And now imagine that I push the piston into the gas. Well, the energy is not going to be conserved. In fact, energy is going to be going into the system. But that has nothing to do with dissipation to any kind of environment because there's no environment involved in that stage of the process.
So what happens to friction or when you push?
Well, what do you mean by what happens to friction?
When you push, you're putting work on the system, there are going to be some friction across the edges of the piston.
Well, let's see, how do I want to put this? I'm assuming this is a system that's evolving under Hamilton's equations. Friction is something that you can almost think of it as an emergent phenomenon that comes out of Hamilton's equations. If I'm specifying that this is evolving under Hamilton's equations, then that fully specifies the microscopic dynamics of the system. I don't have to put in any friction by hand and so on. Okay. Now, if it's it's a complex system with many degrees of freedom, I know that generically, when I push the piston in, there will be some shock waves, and those shock waves will, so to speak, dissipate due to internal friction. But that's, in principle, all captured by Hamilton's equations. All right? That's a consequence of a many degree of freedom system evolving under Hamilton's equations. You look confused, but I have a feeling that I probably won't be able to answer any further confusion in a reasonable amount of time. So maybe we can talk about this offline. Okay, so at the moment, though, I'm still working on something that has no dynamics in it. I've just looked at this mapping. Now I've gotten to this point where this average is now given by this expression over here. But because there's a one-to-one relationship between points x and points y, I can change the variables of integration from x to y, and I know how to do that. So that's going to be, I'm going to replace the dx here by dy, and then I have to throw in the Jacobian associated with that transformation of variables of integration. And now I can just write the integrand as e to the minus beta h sub a of y. All right, so in this expression, y was the dependent variable and x was the independent variable. Now I've made y into the independent variable. Okay, and here's where Liouville's theorem comes to the rescue. This is equal to 1. All right, and what's left over is just this integral of the Boltzmann factor, and that's just the partition function. Right? So this ends up being z over z, which is equal to 1. All right. So the average of this quantity under any such mapping is going to be equal to 1. And now we're almost there because there's mathematical inequality, Jensen's inequality, that tells us that the average of e to the x is always greater than or equal to e to the average of x. Right? If you're not familiar with this, there's kind of a simple proof of that somewhere later on in the notes. But take it on my word for the moment. So if I now combine this inequality with that equality, I have e to the minus beta phi is greater than or equal to e to the minus beta times the average of phi. Pardon me? No, I think this is still correct at this point. And if I realize that this quantity, that this average over here is equal to 1, then this immediately implies that the average of phi must be greater than or equal to 0. Okay? So again, I've shown that this inequality can be established for any mapping that satisfies these conditions over here. And now the final step in the proof is to realize that evolution under Hamilton's equations constitutes this kind of a mapping. So initial conditions get mapped to a unique set of final conditions. So my mapping now is going to be x0 to x of tau, where this is the mapping that I get by evolving under Hamilton's equations. Right. So this tells me that if I sample initial conditions from canonical distribution, evolve under Hamilton's equations, then on average, this phi is greater than or equal to 0, which is another way of saying, on average, the final energy is greater than or equal to the initial. Okay, so that's how this proof goes for the canonical ensemble. As I mentioned, for this kind of macro canonical ensemble, that's left as an exercise for you all. It's actually not particularly mathematical, not particularly difficult mathematically. And for the microcanonical ensemble, this just isn't really general. Okay. Yeah.
If you compare the system as a continuous system, and
as a what?
If the system is compared with
is preferred in the canonical system. And then when you begin to do the one-shot system, and you need to let the system be an isolated system. But then in this case, if the system becomes an isolated system, it should not be a canonical system anymore. So,
well, what do you mean by it should or shouldn't be a canonical system? The canonical ensemble that I'm describing here reflects how I prepare the system's initial conditions.
Yeah,
all right?
you can.
So if I take the system, place it in contact with a reservoir, all right, and then remove the system and place it over here, then take another copy of the system, do exactly the same thing, place it over here, and do that many, many times, I'll have a number of copies of the system, and they will have the distribution of energies will be described by canonical ensemble, just because of the way I've prepared this, right? Each of those copies is now perfectly isolated, and I'm perfectly justified in asking what happens if now I allow each of these isolated systems to evolve as I'm changing some parameter. Just because they're isolated, this ensemble doesn't suddenly match up so that everybody has the same energy. So I think part of the confusion I think here is that when people associate a microcanonical ensemble with an isolated system, the reason for doing that is that if you think of one copy of a system, right, and it's an isolated system and you're not changing any external parameters, and you watch how that one copy evolves with time, then with time, that one copy will explore a region of phase space that's consistent with the microcanonical ensemble. All right? But here, this x of a of x0 is not meant to represent the distribution that a single isolated copy of the system explores with time. Rather, this is meant to represent the distribution of initial conditions that depends on how I prepare the system. Okay. Let me move on to kind of the main subject of these lectures, which is going to be non-equilibrium work and fluctuation relations. And just to remind you of the physical context here, so remember that picture that's drawn up all the way to the left of the single-stretched molecule. So I'm going to be considering processes where I subject this molecule to either a forward or a reverse thermodynamic process. So in the case of the forward process, I start in equilibrium state A, I change lambda from the initial value A to the final value B, and I allow the system to relax. This happens over some period of time that goes from 0 to tau. And the reverse process is defined in a similar manner, but with B going back, the lambda going from B back to A. Okay? And as I mentioned yesterday, just based on what we know from the macroscopic second law of thermodynamics, we would guess that the distribution of work values that I would get during the forward process and during the reverse process would look something schematically like this. So there's going to be some fluctuations around the average in each case, but on average, the work during the forward process is going to be greater than or equal to the free energy difference delta F, and minus the work during the reverse process is going to be less than the free energy difference delta F. And again, that's just what I mentioned. That's just what I went through yesterday. But now, what about the fluctuations around the average? So it's tempting to kind of look at these and think, well, these are just kind of boring, uninformative noise. They don't really tell us anything interesting. And kind of the punchline here of my presentation is that that's not the case. That actually that these things satisfy some fairly strong and fairly unexpected laws. And in particular, these non-equilibrium fluctuations, because again, these fluctuations are here because we're driving the system away from equilibrium. These non-equilibrium fluctuations actually contain equilibrium information inside them. So we can use these distributions to determine equilibrium properties of the system, such as free energy. So,
can you do that in the reverse? Can you then take equilibrium properties and extract non-equilibrium information?
Not necessarily, no. I think it's... I wouldn't know how to do it. Pardon me?
You can only do it in one direction.
As far as I'm aware. Okay, so let me start by just mentioning three of these work relations, and these are the ones that I'm going to focus on. So the first is the following. let me imagine just focus on the forward process, and let me imagine that instead of looking at the average value of the work, which would be kind of the intuitively natural thing to look at, I'm going to look at the average value of e to the minus beta w. So again, what I mean by this is the integral over this distribution of work values that I get by repeatedly stretching the molecule over and over again of the quantity e to the minus beta w. So that's just what I mean by that average. And the claim is that this average is actually going to be equal to e to the minus beta delta f. Right? So that's the first prediction. And the claim is that this is true even if the system is getting driven far from equilibrium during the process. So this isn't just some kind of near equilibrium linear response kind of prediction. Question? Okay, so that's the first prediction. And let me just mention before going on two particular consequences of this prediction. By Jensen's inequality, remember the average of e to the x is greater than or equal to e to the average of x. This equality immediately implies that W is on average is greater than or equal to delta F. So this is in no way inconsistent with the second law of thermodynamics. Moreover,
so this actual value of W.
Pardon me?
This actual value of W. You had W forward and backward.
Oh, so right now I'm just considering the forward process. I'm just considering one process, right? So I should be putting subscript after here, but I'm just considering one process. So it's telling us basically that the mean of this distribution must be greater than or equal to this value of delta F. It also turns out that from this equality, one can immediately show that this tail down here must decay exponentially or faster, right? And that's again consistent with kind of our macroscopic observations that violations of the second law are extremely rare, or essentially impossible for macroscopic systems. And I'll go through both of those inequalities in more detail later. All right, the second prediction that I'm going to discuss involves now both the forward and the reverse process. And it states that the distribution of work values during the forward process divided by the distribution of minus work values during the reverse process for some particular value of W, that this ratio of distributions is exactly equal to e to the beta W minus delta F. And this was derived by Gavin Crooks about 10 years ago when he was a graduate student. So this is a very interesting, very unexpected, I think, symmetry relationship between this forward distribution and the reverse distribution. I mean, keep in mind that the shape of these two distributions depends very much on how we're carrying out the process. If we carry out the process relatively slowly and gently, then these two distributions are going to be peaked more or less around delta F. Whereas if we carry it out very rapidly, then they're going to be much broader. But this equality, this prediction says that no matter how we do it, these two distributions are always going to be related by this kind of simple symmetry relation.
What if you do another forward process but maintain detailed balance? Then everything would be also.
I would have to ask you to explain what you mean by detailed balance. In one of the proofs that I'm going to give of this, I actually do assume that detailed balance is maintained, but that's not the same as saying that the system is in equilibrium.
So essentially, it has essentially the same properties.
When I say detailed balance is satisfied, I mean that the dynamics are satisfied detailed balance, which means that the system would relax to equilibrium if I started out in a non-equilibrium stationary state. So for instance, in my definition, Hamilton's equations satisfy detailed balance. Right, but still I can take a system, a Hamiltonian system, and drive it away from equilibrium by acting on it, with an external parameter like pushing the distance.
Your first expression is you average over W, right?
Well,
but if you would do like before, in the clinical group, the starting position is the same situation to be valid. If you put there just the average over the starting position, instead of
Well, it is the same thing. This is really these angular brackets means an average over infinitely many repetitions of the experiment. So I am averaging over all sets of initial conditions. All right. But because the quantity that I'm averaging depends only on W, that's my choice to look at this particular quantity, I could write that average like this. But really what these brackets mean is an average over all initial conditions, and or more generally over infinitely many repetitions of this process.
Chris, but the difference between this and what you just talked about before, where it equals to 1, is that this is not isolated system?
In general, this is true for. In general, this is going to be true for non-isolated systems.
Right, because you just showed us that average of 1.
Right? This is not a cyclic process.
Oh.
Here, I was talking about cyclic processes. So, in some sense, what I was doing here was a special case of this under two assumptions: it's an isolated system, and it's a cyclic process.
Is this true for all W's or just for the W and E?
W what?
Is this true for all values of the work W, or is it true only within E? I mean, this ratio of the two.
No. This is true for all values.
For all of them. For the entire distribution.
Yeah, for the entire distribution. Now, basically, if I were to divide this function by this function at any point, I'd have an exponential.
Okay.
And by the way, one way to think about this equality is the following. In macroscopic thermodynamics, there's this statement that for any reversible process that gets you from state A to state B, the work is going to be equal to the free energy difference, no matter what path you take in parameter space, for any reversible process. This is kind of an analogous statement, but it holds for irreversible processes as well. So for any irreversible process that takes you from state A to state B, this particular average is going to be something that depends only on the initial and final states, A and B, and not on how you get from one to the other. Okay, so let me just briefly mention two consequences of this. So one consequence is that these two distributions cross exactly at delta F. Somebody pointed that out yesterday, and you can see that because you ask where these two distributions cross. Basically, you're setting the left side equal to 1, and that happens when W is equal to delta F. So that's a kind of satisfying result. That no matter how you're carrying out the process, those two distributions are always going to cross at exactly the same point, and that point is equal to the free energy difference delta F. And another consequence of this equality is this equality over here. And I show you that in the notes, basically to bring this the denominator here over to the numerator up here, multiply each sign by e to the minus theta w, and integrate. You get exactly you get back exactly that equality. So the third prediction that I'm going to mention is a little bit more complicated. So let me write it up here, and I'm going to write it like this, and then explain what I mean by this. Delta of x minus x of t e to the minus beta w's of t 1 over z to a e to the minus beta h of x and lambda. All right, so let me explain what's going on here. So the x here is an independent variable. So what I'm saying is that this is true for any position x in phase space. X of t here denotes some trajectory. So I have some trajectory that the system is following during one realization of the forward process. So again, I'm only considering one process here, just the forward process. So this is one particular trajectory, and w sub t denotes the work. So this is some time t here. W sub t denotes the work that's performed during that trajectory up to this particular time t, right? So the trajectory starts at some position x0, and there, by definition, the work is 0, and then as the system goes along, work is being performed on it, and Wt is the work performed up to this time t. Beta has the same meaning as before. It's the inverse temperature of the equilibrium state in which the system is initially prepared. And on the right-hand side, you have something that looks like a canonical distribution, except it's not properly normalized. So you have the Boltzmann factor associated with the value of lambda at time t, divided by the partition function associated with the initial equilibrium state of the system. Okay? So roughly a way to interpret this to interpret what this is what this is saying is to think of the left-hand side as kind of a weighted ensemble in phase space, or a weighted phase space distribution. It's basically telling you that if you consider this ensemble of repetitions of this process, you can think of that as a swarm of trajectories evolving in phase space. That swarm of trajectories is initially in equilibrium because that's how you prepared it, but then as you start, pushing your piston in or manipulating your parameter, this swarm of trajectories gets driven away from equilibrium. And the claim is now that if you just simply attach a time-dependent statistical weight to each one of these trajectories, where that weight depends on the amount of work that's been done on the system, then by attaching that weight, you immediately recover the equilibrium distribution corresponding to the current value of the parameter lambda, apart from this incorrect normalization. Right? So in other words, it's telling you that from this swarm, by observing many repetitions of a system driven away from equilibrium, you can reconstruct the equilibrium states along the entire path of parameter.
Just to verify something, you probably said that the only assumption we're making here is that the initial state is prepared with a canonical distribution.
Right. Well, yes.
And then we just do some work and see what happens. And when we say we have a delta F, we have free energy at the final point, that we don't say we're actually equilibrating our system. That would be the free energy if we hadn't.
Exactly. Yeah. So I'm assuming the canonical distribution of initial conditions. That's very important. I haven't actually specified here what I assume about the dynamics. All right. So this is not necessarily for an isolated system, and I'll get to that. In a moment. But again, the free energy, in fact, let me write down explicitly, the free energy as a function of the parameter lambda is, I'm defining this to be minus kt times the log of the partition function associated with that value of lambda, and the partition function is just an integral of the Boltzmann distribution. So that's how free energy is defined in the system. And physically, again, the F sub B would be the free energy of the equilibrium state if the system were allowed to relax back to a state at that value of lambda in that particular.
So average is done over with the Boltzmann weight. Can you explain again what is the average?
The average is an average over trajectories, over this ensemble of trajectories.
So the initial states are Boltzmann distributed.
The initial states are Boltzmann distributed, so that's where part of the average comes from. Moreover, if the evolution itself is not deterministic, which it will be in some of the models that I will use, if the evolution itself is not deterministic, then you have a further averaging over all the different trajectories that might evolve from a given initial point in phase space. If you're assuming that this is Hamiltonian evolution, then the only averaging is over initial conditions, because everything's deterministic. So let me make a question.
Could you clarify? Is there tau or is it t everywhere? Or?
This is for all values of t.
Okay. So on the right is lambda t.
That's right.
So at some point you say stretch to some particular lambda.
Yeah. So this is a time dependent thing. Okay. Right. So in fact,
we have to see for tau and the regular access over there, and then in this case, the average is an average of law.
Yeah. Exactly.
It's the same as average.
Yes, yeah. So if I integrate both sides over x, then I have just an average of e to the minus beta w sub t, and that can be expressed as an average of rho of w sub t. Exactly. So in fact, if I evaluate this equation at t equals tau, and I integrate both sides with respect to x, again I come back right to this result.
Well, because of ZA and ZB, right?
Pardon me?
Because of ZA, delta F is ZA minus ZB. ZB over ZA.
That's right. Delta F is going to be, right, e to the minus beta delta F is Z sub B over Z sub A. And let's see. So I have a kind of picture on page 17, which is meant to kind of give you an idea of how this is supposed to be interpreted in terms of these weighted trajectories. But in the interest of time, I'm not going to go through that. And let me kind of wrap up, since I'm basically done, my hour. Let me wrap up today's lecture by giving you an idea what I'm going to be, where I'll start with tomorrow. So all three of these predictions are exact results, within the assumptions that are made to derive them, and I'll spell those out. They're valid, so in particular, that they remain valid far from equilibrium. They place, as I mentioned, some strong constraints on the distribution of work values that are obtained during the process. They tell us that these non-equilibrium fluctuations in work values encode equilibrium information, such as free energy differences, or indeed such as the entire canonical equilibrium distribution. And these are closely related to some to earlier results. So in particular, back in the late 70s, two Soviet scientists, Microscopic and Liouville, derived a similar result to number one, and actually to number two as well. I'll write their result as e to the minus beta w prime is equal to 1. So they used a somewhat different definition of work, and using their definition of work, this particular value isn't equal to the exponent of the free energy difference, but it's always equal to 1, regardless of whether it's a cyclic process or not. So this was, I think, first done in 1977. Moreover, all of these results are closely related to so-called fluctuation theorems for entropy reduction. All right, so again, all of these are discussed in terms of the work performed on the system, but there's an entirely different set of results that are analogous to these that are discussed in terms of the amount of entropy that's produced during the process. And I'm not going to go into any of that, but I think you'll hear a lot about that from Udo Seifert next week, because he really has a very, very nice way of placing all of these different results, the work results and the entropy results, under one kind of theoretical umbrella. So what I'm going to start off next time is giving you derivations of these three results, and I'll give different, so whenever you're talking about deriving a result for some microscopic system being driven away from equilibrium, the starting point has to be, well, what equations of motion am I going to use to model the evolution of the system? There's always going to be, I always have to make that choice. So I'm going to show you how to derive this equation under the assumption that that the evolution is determined by Hamilton's equation, so Hamiltonian evolution. I'm going to derive this this prediction under the assumption that the system evolves in discrete time steps according to a random Markov process, and I'll explain that in a little bit more detail tomorrow. And if I have time, I will derive this equation using the Feynman-Katz formalism, the Feynman-Katz formula of statistical mechanics. And that basically follows a derivation of this result that was first given by Gerhard, Hummer, and Attila Szabo about 7 or 8 years ago. So let me end my lecture at that. I'll start off with the proofs of these things tomorrow, and any other questions I'd be glad to take them now.
Is there any questions?
Yeah. Can you say something in general about the actual formula of the work distribution? Like each problem is a different thing?
Generally, yes. The main exception to that is if you are in the near equilibrium regime, then there are generic arguments that would lead you to expect that the distribution is Gaussian. Right? But apart from that, no, there's not. I don't think there are really any very general things you can say about the distribution.
Even the distribution?
No, well, as I kind of briefly mentioned, this equality tells you that the area underneath these tails dies exponentially or faster, and that's quantified in the notes. But apart from that, I don't know what to do.
In your statistical derivation of second law, you distributed your initial conditions according to some weight, say Boltzmann, then you isolated each system and then what if you don't isolate? You just keep it in front of that.
Okay, so you're talking about now generalizing that proof. It depends on what you choose for your initial condition. So what I can say is, okay, I've got my system of interest and then my heat bath, right? Let me consider the two together as some much larger isolated system of interest. As a much larger isolated system. if I choose my initial conditions for that larger isolated system from a canonical ensemble in the larger phase space, then the same proof goes through automatically. If I don't, then maybe not. So that would have to be, you have to tell me how you're setting up the system.
Okay. So for the RNA experiment, you have to assume a Hamiltonian that you can evaluate during the process.
Well, yes, I assume that the system is described ultimately by a Hamiltonian.
So you have to give in the form of a Hamiltonian to evaluate the work. It's not just force times displacement, but...
No, it depends. So here's what's going on specifically in the context of the single molecule pulling experiment. The Hamiltonian in that case will have two components to it. One is the Hamiltonian that describes the interaction, within the molecule itself, right? And that's going to be something, fairly complicated. You don't really want to deal with that. But then there's going to be part of the Hamiltonian that describes the interaction of the bead with the laser trap. And that's going to be the only part of the Hamiltonian that depends on lambda. Okay? So when you write down your expression for work, it turns out that's the only part of the Hamiltonian that matters. So it does reduce to an integral of force times d lambda, basically. So there you're saved by the fact that you have this particular setup. But in general, theoretically, you need to know the entire Hamiltonian.
Some questions related to Sid's question, which is that if you want to produce a particular row, can you say anything about what protocol you need?
No, and that's a question that's going to be so system specific that, and even for a particular system, no, I would say, integrate your equations in motion and see what comes out. So again, none of this really has much predictive power about what these look like. But they tell you, for instance, that once you know the distribution of forward work values, you know the other one, right? And vice versa. But it doesn't tell you either one.
I mean, from the experimental point of view, it'd be nice if you have some way of controlling work by controlling your protocol.
Well, you certainly influence rho by doing different protocols. So I can tell you generically that the slower you do the system, the more narrow it is. But so you have that influence, but I can't give you an explicit form. Generically for complicated systems, this isn't going to have any kind of nice closed form. I mean, there are a handful of exactly solvable models where you can determine these things, but those are exactly solvable models. So those are very simple.
Any other questions?
So here we use the tail balance to derive these constraints in the dynamics.
In step 2, I will.
Yeah.
Explicitly, not in step 1. Yeah.
So do these constraints put some constraints in the dynamics itself? So if this is true in the experiment, can you say something about the dynamics of the system?
I'm not sure what you're saying. What do you
Suppose I'm a little bit experiment some system and I find that result.
Okay, you verify it. Okay.
What can I say about my system? What can I say about the dynamics?
Really not much, because in some sense, okay, just because I'm going to be proving this using detailed balance doesn't mean that that's the most general proof. So I do have a proof, which I'm not going to go through in full detail, but I do have a proof where you model the system and the reservoir together as a Hamiltonian system, right? So under the assumption that the system and the reservoir together can be described by a classical Hamiltonian, all of these results are valid. So in some sense, if you do your experiment and you find that, then you verify that your system and reservoir act as a large Hamiltonian system. So I'm not sure if that's what you would expect. You would expect from so I wouldn't say that this kind of that you divide processes into those that satisfy this and those that don't, and you learn about the process whether or not it's satisfied. Generically, I think these will be satisfied in principle, although in practice it might be very difficult to verify. Does that answer?
Can you please comment on the convergence properties of exponential letters?
They're very, very ugly. So the idea is, the question is, all right, if I'm taking the average of this, how quickly does that average converge? How many samples do I need to take? without trying to justify my answer, let me just give it over here. So if I'm trying to take this average over this distribution of work values, I have to sample from this distribution sufficiently many times that I end up sampling the region of the work values that are typical of this distribution over here. All right. So these two distributions are, by and large, have very little overlap with one another, which will typically be the case for large systems. That means I'm going to have to sample very, very deep into the tail of this system in order to get this to converge. That's why these results are somewhat formal results for any macroscopic systems, because the number of samples you need to take is, enormous. Roughly, it grows exponentially with the size of the system. Very, very roughly.
It gets better closer to equilibrium.
That's right. It gets better closer to equilibrium.
Just to continue on that, to take so many samples, what is the experimental verification?
So the experimental verifications, and maybe you'll hear a little bit more when Shiva does her lectures. The experimental verifications are using single molecule pulling experiments. So those are not macroscopic systems. Those are microscopic systems where the fluctuations are enough that you can observe this. So in those kinds of systems where people actually do these get these distributions, there is a certain amount of overlap between the distributions that they actually see in experiments. Whereas if I were to actually try to get these distributions using a rubber band, I would never see any of them. Okay, it's there, but it's exponentially deep in the tail, and so I'm never going to observe that. So all of the verifications are for microscopic systems driven.
Okay, maybe one last question.
Is there a connection between 3 and 2?
Not a direct, as far as I know, not a direct connection in the sense that you can't derive 3 from 2 or vice versa.
Okay, let's thank the speaker.